Alright, so today we're going to have a look at roots of complex numbers and solving z to the power of n equals c. So that might not mean anything to us at the moment, but we're going to have a look at this. So, solving z to the power of n equals c. Basically, the nth roots of the complex number c are the solutions of z to the power of n equals c. Alright, so for example, the fourth roots of 2i, so instead of having c, we've got 2i, and instead of having n, we've got 4, are the four solutions to z to the power of 4 equals 2i. Okay, I think this is probably one where we're going to have to see an example first, but I'm still going to run through some of the vocabulary beforehand. All right, so let's have a look at some more of the vocabulary and the rules. So solving z to the power of n equals c, there are exactly nth roots of c. So whatever this number is, if it's z to the power of 5, there's 5. Z to the power of 10, there's 10. Whatever this number is, that's how many roots there are. If c belongs to the real numbers, so if c is belonging to a set of real numbers, the complex roots must occur in conjugate pairs. Okay, so what that means is if you find a root and it is 1 plus 4i, that means the conjugate pair of that is going to be 1 minus 4i. Okay, if next part, if c does not belong to the real numbers, then the complex roots do not all occur in conjugate pairs. All right, so then this here does not have to necessarily happen. All right, next up, the roots of z to the power of n all have the same modulus, so they all have the same length, which is the length of c, the length of our complex number, to the power of 1 on n. On an Argand diagram, the roots all lie on a circle with radius c to the power of 1 on n, okay, which makes sense because these all have the same modulus, so they'll lie on a circle. The roots of the circle r equals the modulus of c to the power of 1 on n will be equally spaced around the circle. If you join corresponding points, you will obtain a regular polygon. So we'll have a look at that in a minute as well, but those are the rules we might revisit later. All right, so let's have a look at what this actually means. So find the fourth roots of 1 by a factorization. So we'll start with that. So when we have a look at this, we're going to do z to the power of 4, because it's the fourth root, so z to the power of 4 of 1. All right, so the first thing we're going to do is we're going to do this by factorization, and then we're going to use the nth roots methods. So the first step here, we're going to use factorization, so we're going to bring the 1 to the other side, so we get z to the power of 4 minus 1 equals 0. All right, now you may or may not be able to recognize this straight away, but when we have like a squared term, take another square term, so 1 is a square term, we can do factorization. So I could rewrite this as z to the power of 2 squared, take away 1 squared. Okay, so if I was to rearrange this, I would write it as this first part, so z squared take 1 multiplied by z squared plus 1. All right, and if you expand this out, we're going to get z to the power of 4. The cross terms cancel, and we're going to get 1 times negative 1, which is negative 1. All right, so that is the first part of this factorization, but we can do another. Okay, so because this number here multiplied by this one equals 0, either one of these things has to be 0. So if z squared take 1 equals 0, it means that we must have, to factorize it, z plus 1, z minus 1 has to be equal to 0, factorizing that. And on this side, we're going to factorize out z plus I, z minus I equals 0. All right. So what we've done, we've just factorized a couple of times. So this is just straight from like year 10 maths, except now we've got some i's in it. So what this means is if this thing equals 0, that means the z equals -1, +1, -i, or +i. Because if you put -1 into the first part, -1 + 1, that's 0. If you put 1 into the second part, that's 0. So if any of these numbers go in, they're going to make a total of 0. So we could rewrite this as z equals ±1 and ±i. All right, so this here is the answer. So what this means is we've got z to the power of 4, we've got 4 roots, so we're going to get 4 solutions, which we have here. If we go back to our previous answer, so there's exactly n number of roots, so we've got exactly 4 roots. If c belongs to the real numbers, which it did, it was 1, it must occur in conjugate pairs, which they do. If c doesn't, so it did belong, so that we can't see that. If the roots of Zn will have the same modulus, so all of ours do have the same modulus, they're just 1. So our original term had a modulus of 1 as well, so that's why. On an Argand diagram, all the roots lie on a circle with radius of 1. So if we were to draw our roots on a circle, we've got +1, +i, -1, and -i. So we could draw a circle out that encompassed all of them with a radius of 1. All right, and our last rule, the roots on the circle will be equally spaced, which they are. If you join corresponding points, you will obtain a regular polygon. So if we joined ours here, we would obtain a polygon with 4 sides, also known as a square. Okay, so hopefully that is just a little bit clearer. We're going to have a look at the nth roots method now. All right, so let's have a look at the nth root method. So if we start with, again, z to the power of 4, oops, my pen's just not working there, equals 1. So according to the nth root method, we could rewrite this as, if you look on our unit circle, the only time this is going to be 1 is if we're at an angle of 0, or 2 pi, or 4 pi, etc. So we can rewrite this as z to the power of 4 equals cis, and we know the length is 1, so we can just put a 1 out the front or just leave it. Cis of 0 plus k lots of 2 pi, where k belongs to our integers. All right, so that's the first step. So we can simplify this a little bit further because we know that 0 does not add to this, so we've got cis of k 2 pi. Now at the moment we've got z to the power of 4. If we want to get rid of that, we're going to have to put both sides to the power of 1/4. So cis k 2 pi all to the power of 1/4. Put a big bracket around there. All right. And what happens on the left-hand side is it becomes z to the power of, we multiply when there's a power to a power. So 4 multiplied by 1/4 is 4 on 4, which hopefully you can see will go away. And cis. Now, using de Moivre's theorem, we know that this is going to multiply our modulus, which is just 1. So we can just ignore that. Sorry, not multiply, it's going to go to the power, which is 1, so it's going to become 1 to the power of 1/4. Cis, lots of, and it multiplies this argument in here. So k 2 pi multiplied by 1/4. All right, z to the power of 1, 4 and 4 just becomes z to the power of 1, just z. 1 to the power of anything is just 1. We're going to get cis of k 2 pi over 4. All right, and we're going to say this step here, the reason we were able to do it is because of de Moivre. Because it's really important that we write the reasons we do things to show the people looking at our work why we've done any of it. All right, so the next point, this is probably the most important step here. So we're going to say let k equal, we've got 4 roots, so we're going to choose 4 numbers. So 0, 1, 2, and 3. We're going to choose 4 numbers. So what this means is we'll get 4 solutions as well. So we're going to get, the first solution is going to be z equals cis of 0. Second solution is going to be z equals cis of, put 1 in, so it's going to be just 2 pi on 4. Now, if you've written pi on 2, that's the same thing as well. All right, the next is going to be z equals cis of, substitute 2 in for k, so 2 times 2 is 4 pi over 4, which is just pi, cis of pi. And finally, z equals cis of 3 times 2, so 6 pi on 4, which is the same as 3 pi on 2. All right. Now, if you go to 0, what you're going to get is you're going to find on your unit circle, go to 0, you're going to find that z equals 1. If you go to pi on 2, you're going to find that it equals I. If you go to pi, it's going to equal -1. And if you go to 3 pi on 2, it's going to equal -I. All right, those are all the points on the unit circle that we go to, because this is 0, this is pi on 2, this is pi, and this is 3 pi on 2. All right, so we're just left with those points, and it's exactly what we worked out for factorization. So that's the nth roots method and factorization. So we'll have a go at a few of those now.